You may wonder why I put this up here. This is the Munich Olympic Stadium of 1972 with this beautiful structure, and that's minimal surfaces. And there's a story behind that. The story goes back to what happened at the TU Munich quite some time ago. There was an engineer. Here you see his picture in 1880, and Alexander Brill, and he asked his students to design all kinds of interesting shapes and put soap films on them, and to illustrate these things at the minimal surfaces with different frames. This was brought to a World Fair, and you can see these things now in the Smithsonian. They have been bought and they're now exhibited in the Smithsonian as a history museum. So that's the story behind. And the point really is, if you dig deeper into those minimal surfaces, a lot of beautiful physics that goes along with it. And what we do today is just a simple example of such a surface tension and minimal length phenomenon. So let me go back to the board and talk about interfaces and what's also called domain walls in these systems. So usually you have states phi plus minus being square root of r over u being the two stable states corresponding to domains which are all plus or domains that are all minus. So all is spin up or all is spin down with some thermal fluctuations around it, so this is not quite one. Now, a solution that we saw happens in these systems is that you have the regions with spin up and spin down separated by interfaces as blue and red regions. These are the interfaces I was talking about, or the domain walls between spin up and spin down. And what we want to study now is, can we infer from the equation of motion an equation for such an interface? Do we know how it looks like, how the spins turn from up to down? And what's the width of that interface? And can we specify how this interface evolves in time? It's a very classic example of coarse-graining, where you start from a partial differential equation of field theory, and now you try to project the field theory and find a solution for a meta-excitation for an interface. So let me explain how this works. And the first thing I asked myself is, what is the steady state condition for a Allen-Kahn equation? The steady state condition simply is that there is no time evolution for the profiles, for the density profiles. And that means the right-hand side has also to be 0. So kappa dx squared of phi minus f prime of phi is 0. And as you, I guess, noticed, I have now dx instead of a nabla. And what I'm doing now is I'm looking at a straight interface along the x direction, really assuming I have something that is not bulged out, as I showed it in the white color, but it's actually straight. I later come to what happens as I have curvature in this interface, but now let's look at a straight interface. Okay, so this is the steady state condition for a straight interface or straight domain wall. Good, that's the equation. And now let's construct the solution. And in order to construct the solution, it's very important to first non-dimensionalize the system so you see what you can read off the equation already by dimensional analysis and what's then later the property of the profile intrinsically. So what we do first is we say we rescale our field by pulling out the absolute value of our field. So we rescale by the amplitude because that's the basic amplitude anyway, and I want to rescale now between -1 and +1, and that's why I pull this out. And I call the rescaled field phi tilde. That's now varying between plus and -1 and not between plus and minus square root of r over u. Okay, and also what I do is I shift f of phi up and down, right? I can do this because that's just determining the minimum or the reference point. So I'm shifting it up such that I have the minima of the potentials being right at 0. So they touch 0 right where you have the thermodynamically stable homogeneous steady states. And when we do that, we can rewrite our free energy function, the density, as r over 2 phi plus minus squared phi twiddle squared plus 1 squared and phi twiddle minus 1 squared. And now you see clearly what this function is, right? This function has two minima. One is a plus and minus 1. And maybe it's now even more clearer than the original phi to the 4th term. And that prefactor here in the following I just call A. Right? I want solutions that ultimately, if I'm far away from the perturbation, will approach the equilibrium steady state, so phi plus and phi minus. And the choice I'm taking is that as x goes to plus infinity, I want it to approach phi twiddle plus equals plus 1. And as x approaches minus infinity, I want to approach it the corresponding steady state value phi minus. And then there will be some interface, and I'm now guessing it, and later we calculate it. So I will have some interface going from here to there, and I've made a convention that I want this such that some point, which is here, the inflection point, is right at 0. I could also choose this to be anywhere else, and then I would shift my coordinate system such that this is the case. Okay, so I want solutions which in the limit of x going to plus or minus infinity, phi of x approach phi plus or minus. All right, so that's what I want. And now let's see whether we can find such solutions. And for that, we go back to our steady state equation. The steady state equation was kappa dx squared phi minus f prime of phi equal to 0. Now, when you look at that equation, you can integrate that once. And as you integrate once, you'll get the following structure. You get kappa dx phi squared equals 2 f of phi. And you can check quite easily, just take the derivative of this expression, and you will end up with that equation. Okay? Here you take the chain rule, so this is f prime of phi times the x phi, and this cancels the factor in the right and left, and then you have this expression. Okay, so that's the equation that we have. And now let's go one step further because here we eliminated the amplitude of our fields. And now let's eliminate also the amplitude that gives the variation in space. So introduce a new variable. So introduce a variable that I call x tilde, and it's x times the square root of r over 2 kappa, and I just call this quantity that's in the brackets, in the square root, I call this psi. Okay, and this psi is the correlation length because it is characterizing how strongly our profile varies in space. And one thing you should notice, if you look at this correlation length that I defined here, it's actually diverging when I go to the critical point. There is r equal to 0, and then psi has to be infinity. Okay? And that's a very special point where these domain walls actually cease to exist, because in the end, I want a domain wall to be well defined such that the width is small. If the width is not small compared to system size, I can no longer speak of domain walls, right? So we have to be careful that this analysis here that comes now subsequently is for correlation lengths that are sufficiently small such that we don't go close to the critical point. All right, if you do that, you rescale space and you get the ultimate equation, dx tilde phi tilde squared equals phi tilde plus 1 squared phi tilde minus 1 squared. And you can also write this as 1 minus phi twiddle squared squared. So after these few steps of algebra in making our equation dimensionless and also shifting it in a proper reference frame, the structure you get is a very simple structure, because now you have a differential equation where you say you have dx phi tilde squared is some other function squared. You can take the square root, and then you get dx phi twiddle is plus or minus 1 minus phi twiddle squared. Right? And that has a very simple solution because it's the integral by separation of variables of 1 over 1 minus phi squared, which is a hyperbolic tangent. So by separation of variables, you'll find that the solution of that is plus or minus the hyperbolic tangent of x twiddle. And that's what I basically drew here. So this function that I drew here is just, approximately what you would see if you were to draw a hyperbolic tangent. And as you saw here in the solution, this is x twiddle. And this means if I go back to my original variables, phi of x, then these original variables, this would read as plus or minus square root r over u times the hyperbolic tangent of x over psi. And now you see clearly, right, this psi is the width of our domain wall. The two solutions they are often also called kink and anti-kink solution, because one goes from the left to the right of the minima of the free energy function, and the other one goes just in the opposite, in the anti-direction. So what have we learned? We have learned that our equations that we study not only have the thermodynamic states, phi plus, phi minus, as stable states. There's another metastable state, and this metastable state is a kink or anti-kink solution of our differential equation, so a domain wall. And they are metastable because if you shift this, any position is equally possible. There's nothing that drives you forward or backward in the position of that domain wall unless you have a magnetic field, right? The magnetic field would break the symmetry, and then this domain wall would move out of the picture and be then at the boundary. All right, so we do have this domain wall, but it's not the ground state because, as you see, it has a spatial variation between two domains. This is one equilibrium state, and that's one equilibrium state. This is phi minus, that's phi plus. And here you have deviations from equilibrium, so you have to pay. You have to pay because the first term in my free energy density has a gradient, and there are gradients here, so there's cost from the gradients. And also there's cost from the free energy itself, because this one here is not at the minima, it's somewhere in between the left and the right minimum. So let us now ask, what is the cost of free energy for making a domain ball? And this cost of free energy is delta F, and I'll divide this delta F by the area. So when I look into x direction, the area perpendicular to this is what I mean by A. So this is a energy per surface, and that's the very definition of a surface tension. Gamma is the surface tension here, and I can write the corresponding analytic expression for that. So I have to integrate only in this x direction. All right, so this is dx, and then I have the two terms. One is kappa over 2 dx phi squared. That's the stiffness term I have to pay when I go over such a domain wall, and that's the term I have to pay because the free energy is deviating from its minima. And I do the integration assuming that I have an infinite system such that this domain wall starts very far out to the left, turns, and goes very far out to the right. Okay, what is that expression? Now it looks like when you have a first glance at it that you need to know phi in order to calculate, right? But it's not quite so, because we are lucky here. If you go to the top line and look at the steady state condition, the steady state condition says kappa dx phi squared over 2 is F. So this term equals that term. And that means I can write this expression either alone in terms of this bending stiffness, and then the profile would appear here, or I write it just in terms of f of phi. And let me do that. So if you write this in terms of f of phi, you can write this as I write it down, minus phi s to plus phi s d phi times the square root of 2 kappa f of phi. And what I did here in addition, and that's a step I leave out, I'll leave this for you to show, is that I changed integration variables from x to phi, and then this expression, when you look at it, has a form which does not depend on the profile, because it's an integral over phi, and what it depends on, though, is what the profile of the free energy landscape is between the two minima at phi minus to phi plus here. So our surface tension is a property that is a property depending on what kind of landscape we have, what the parameters there are. Okay, that's very important. The important fact is that you do have a surface tension here. There's a cost for creating a line, and this cost is associated with stiffness and free energy costs. Now that we have this, let me go the next step and let's ask what happens to a spherical droplet. Yeah, please.
So if we had spins in our system, as we discussed, we have a completely phase separation between spins ups and spin downs. So 50% of them up and 50% of them down, right?
Yeah.
Okay.
So, I mean, the complete, if you have at the end, in the very long run, you will just have spins up on average and just have spins up down on average. And here these solutions are metastable solutions when one domain you have mainly spin up and the other one you have mainly spin up, right? And you should not think of this as all exactly up and all exactly down, right? Because this profile here, as you see, goes through 0 and then to a finite value again. So what we're talking about is the mean value of the magnetization as I go through. So you have this disorder region in between where the spins are averaging each other out. It's not a description in terms of individual spins. It's a coarse-grained description in terms of a density where you always think about certain smaller domains which you average over. Yeah? Other questions? All right, I mean, already from here, you know if there's surface tension, you know that if you have a line, it should straighten out. Right? Because the longer you make the line, the more you pay in terms of a surface tension. So it's already clear from this very object that the dynamics of the system has this tendency of minimizing length. Now, what I'll show with the droplet is to give you a more explicit description of how droplets then change size. So let's imagine I have a droplet, and this droplet has a radius r that can depend on time. The interface I draw is not an infinitely thin interface. This interface always has the width psi. So what I should actually draw is something that has a certain width, which is this interface width psi. And I'm now making a first approximation. I'm saying I want the droplet to be already larger, much larger than this interface width. So I can really speak about a droplet. If I don't have this assumption, then this thing will become smaller, right? At some point, the radius and the interface widths are comparable, and then the profiles from the different parts of the droplet would overlap, and I could not speak about a droplet in that sense. All right, so let's say then I have a spherical droplet of the phase phi minus, and I immerse it in a sea of phi plus. So as you go along a certain direction, like so, you would see a kink or anti-kink solution, or here in this case, it's from phi minus to phi plus. Good. So that's the picture. And now what we write down is the Allen-Kahn equation in spherical coordinates what I will assume is that our droplet is perfectly spherical. So the two angles, theta and phi, that describe a sphere are just don't matter here because I have a perfect sphere. And when I write down the Laplacian for a perfect sphere, I only have the radial dependence of the Laplacian. So the right-hand side becomes the radial part of the Laplacian. So this is dr squared in radial direction. There's a second term that depends on dimension. The second term is dimension of space minus 1 over the radius times dr phi minus f prime of phi. Okay. In d equal 1, this term isn't there because there I don't have really a sphere. In d equal 1, it's just a point that I have. Good. Now I have this droplet, and now I'm seeking a solution for that droplet in the following form. So I make an ansatz, and this ansatz says that this function of r and t is a function only of the radius minus r of t, the radius of the droplet. And that's really the basic idea that you have here in order to solve that problem. You say that you want now, instead of a solution for the field as a function of position and time, you want to infer from that a dynamics for the radius alone, for a collective variable. Okay? So r of t is a collective variable, and you want a dynamics for that collective variable by making this ansatz. What does it assume? Any idea? So you have a profile. Yeah, go ahead, please. Yeah, so maybe what you mean is if the time evolves and the radius changes, the profile doesn't change. So any dynamics in the system that gives you a relaxation back to a steady state profile, our hyperbolic tangent solution, this is fast. And r of t, the collective variable, has a slow dynamics on the time scale of the fast evolution of the profile. Okay? This is the key assumption. The profile dynamics is fast compared to the morphology dynamics. I say morphology dynamics, I mean the change in radius. Because here, right, this function phi is a fixed object. I don't change it anymore. I assume it to be something that is the same as a function of time. Good. With this ansatz for a collective variable, I insert that ansatz in the Allen-Kahn equation and just work out the derivatives. And what I get then is kappa phi double prime. So primes are derivatives with respect to the argument, plus kappa times d minus 1 over r plus dr dt times the first derivative of our profile minus f prime of the profile. That's what you get. And the time derivative here of the RDT comes from the time derivative of phi that you have on the left-hand side. And now you see you have an equation where you're almost done, because now there's some dr dt, and you would like to solve that equation for dr dt. It's not quite yet done because there's still this field phi appearing there, something that we want to eliminate somehow. So let me do the following. Let me take what we have here and multiply this whole thing by phi prime, and then integrate over our domain wall. So we integrate over the domain wall from r equals 0 to infinity. Let's do that. So we have then integral 0 to infinity over the radius. Then we have kappa phi double prime phi prime. I have plus kappa d minus 1 over r plus dr dt phi prime squared minus f prime of phi prime. Okay, so what happens to the various terms that we have? If you look at the first one, that's a total derivative. This is integrated just phi prime squared, and you have to evaluate at the boundaries, which are 0 and infinity. So in the core of a droplet and far in the outside of the droplet. In the core, so if you look now at our profile, if that's our profile that we have, then in the core, the derivatives are 0. You're getting flat. There's a plateau. And also outside, you are in a plateau. You are flat. So phi prime at 0 and infinity are both 0 if my droplet is large enough, such that these droplets can actually evolve into plateaus in the inside and outside. All right, so that's 0. And I don't need to worry about that. What about the second term? Well, the second term that we have there can be approximated because we have made an assumption about length scale separation. We have said that the width of our domain wall is small compared to the radius. Okay? So if you take the derivative of that, right, then the derivative of that will be such that you have here a peak, right? This is phi prime, basically. And that means this phi prime is a very narrow thing, basically a delta function compared to the radius that you have. So what it means in this equation, I can take this r here, because it's a slowly varying variable, to be the radius of my droplet, since the phi prime, the support of phi prime, is basically right at the radius. So this becomes kappa d minus 1 over r plus dr dt, and what's remaining here is the integral from 0 to infinity dr kappa phi prime squared. And the last term is minus f of phi, also evaluated at phi plus minus. And again, this last term is 0 because phi plus minus are the minima of the free energy, and I've chosen to minima by shifting my free energy functional to be at 0. So remember, I don't know whether I have it here, this was my convention. By shifting the free energy up, I have chosen the constant such that the minima are at 0. So that's again 0. Now what's this? No? Well, it's the surface tension, right? So we have introduced here this surface tension, and I've told you that those two terms are the same because of the stationarity condition. So the term that I just encircled is proportional to the surface tension over kappa. Right? And then we are done, because once we have seen that, so this is proportional to gamma over kappa. And now we are finished with this calculation and get an equation for the radius. So this implies by time scale separation and length scale separation, psi being much smaller than r, and here relaxation of profile is fast. This implies that we have an equation that's dr dt equal to minus kappa d minus 1 over r of t. And when I reintroduce my lambda, the time scale, then this is the equation that we have. Yeah?
Are the two separations naturally related to each other? Because I would imagine when
You have to speak up, otherwise I don't understand you.
are the time and length separations naturally related to each other? Because when the one voice is small, then I might imagine like it's fine to consider only the small, like only consider.
Okay, now I get you. So you're asking, is time scale and length scale separation really different, or is this basically the same assumption that's underlying both, right? Well, yes and no. If you violate the one, you easily violate the other. For example, if you go close to the critical point, meaning you make the width very large, then you also have strong fluctuations, and your profile wouldn't even come to existence because there are so many fluctuations that would hinder the formation of a domain wall, right? So they're a bit intertwined, but in principle, here I would say they are separate assumptions. Once you go to the case where you have a quench to a low temperature phase, then you know that you have a length scale separation, and then you still need to have the parameters such that time scales are still separated. Right? And that's not the case in the initial phase of the dynamics. It's only the case in the late stage of the dynamics where domain walls actually form and you have the motion of domain walls. Yeah. So that's the effective equation that you can derive for the dynamics of our interface. And that's quite an important equation because, well, what does it say? The velocity of radius, so the velocity radius change, is always negative. And that means any droplet that you have will shrink to zero, whatever its size is. And if you go back, and let us look at the movies once more. So here is not really a droplet, but you may interpret the lower object as one. Let's go to the next. Oops, was too fast. So here you see droplets forming, and they all vanish. And maybe one thing you also saw is, if you look at the droplets, and look at how they vanish, they speed up, right? If the radius becomes smaller, this goes faster. And that's what you also see in this equation here, because that scales like 1 over the radius. Yeah, that's the next thing I want to do is to now look at the general case. So let's say we have an interface that's now curved. I'm now looking from the top down, and let's say I'm having here spin up and spin down domains, or the other way around, spin down, phi minus, and spin up domains. And this is the interface separating those two domains. Now I can characterize that interface by a normal vector. So, and I take here a unit normal vector that's pointing outside from the phi minus region. N squared is 1. So it's a unit vector. And once you have that unit vector, you can rewrite the gradient of phi at the interface, so here on the boundary between the two domains, in terms of that normal vector and derivatives that go in the direction of the normal vector, right? So you can write this as the normal vector times the derivative of phi with respect to z, where z is the normal direction perpendicular to the interface along the normal. So it's the normal coordinate. You can use that to also calculate the Laplacian of that. That's simple algebra. So from that, you get that the Laplacian is the second derivative in the normal coordinate with respect to acting on phi, plus the first derivative of phi times the divergence of our normal vector. Now let's make a similar ansatz. Let's say that now for this general case, phi as a function of all the other coordinates that are not perpendicular, so the coordinates that are defining the interface plane, and the normal, this I mean with the dot and set, that this is again a profile equation that depends on these coordinates in the plane of the surface. And when I'm looking perpendicular to the surface, this is z minus zeta of t. Okay, so it's the same thing as before. I'm now just not using a particular spherical geometry, but a general curved interface. And when you insert this ansatz into the corresponding Erlang-Kahn equation, what you get is minus dz of phi dt zeta of t, just as before, where this was dtr and not here dt zeta. This is equal to kappa dz squared of phi plus kappa dz phi, divergence of our normal field, minus f prime of phi. Right? Now, when we look here again at our equations, this one here is the steady state condition relating the second derivatives. Okay, either here, okay, relating the second derivatives to f prime. That we have here also on the right-hand side. Here we have the second derivative of phi and phi prime. So those two terms, they cancel. And this is again the steady state assumption that our system relaxes very fast in the profile, but slow in the collective coordinate. steady state assumption for the profile that you make here. And then you can cancel off these terms, right? This is the prefactor here. That's a prefactor there that I can cancel off from the right and left-hand side. And then the velocity of my interface, dt theta, is given by minus kappa times the divergence of the normal field of our interface. From differential geometry, you know, or I tell you what the result is, that the mean curvature of an interface, two-dimensional interface, is minus a half times the divergence of n. And this is, as I said, the mean curvature. So if you look at an interface, so like so, something that has these structures, if you look here at a point and you measure the curvatures C1 and C2 of that interface, then the divergence of the normal field on that surface is proportional to the sum of the two curvatures, the two principal curvatures on that surface. So what you get from that is a geometric law that says that dt theta that you have here is minus kappa times C1 plus C2. So you have a time evolution of an interface which is dictated simply by the geometry, the curvature of the interface. That's all that is in that equation. And the driving factor that you have in front of it is the stiffness of spatial variations. And that should be clear because the spatial variations cost you something, and that's ultimately driving the motion of these domain walls or interfaces. And that you can check again if you look at these movies. The movies are only in one dimension, in 2 dimensions, so you can't see an interface membrane, you just see an interface line. So there's just one curvature and not two. But if you look again, curvatures of one or other direction move either in or out, that you see on the left. Once the curvatures are gone and things are flat, the velocity goes to 0 because the velocity is proportional to the curvature. And now as things progress, curvature goes away more and more and more. The dynamics slows down ad infinitum to become slower and slower and slower. The same here, which is just a different initial condition where you also have a dynamics where you have these interfaces. They are now basically droplets, but here you see the same thing. Different curvatures move in different directions, and the system ultimately shrinks to 0 with droplets vanishing. All right. So the main thing I wanted to show you today was if you analyze a dynamics of the simplest model you can imagine, a scalar field theory for an Ising model, you can understand the phase transition as an instability phenomenon where long wavelength modes grow. And then once these long wavelength modes grow, you enter a different phase of dynamics that's dominated by nonlinear excitations. And these nonlinear excitations are interfaces. In order to understand what's the physics of it, you need to derive a theory for the interfaces. And that's what I've done. So this is basically the main formula at the end. This is the interface theory in an approximation where you separate time and length scales. It's really a blueprint of many different types of analysis that you do for collective phenomena, because in the end, you want to understand not just the onset of phenomena, you want to understand the long-term, non-equilibrium, steady-state type of behavior. And for that, you typically always need to identify what is the collective variable. Here it was interfaces. In other systems that we learn about later, it could be topological defects and similar kind of excitations. All right. Thanks for your attention.